Okay, so in this video I want to tackle a very important sum. That's the so-called Basel problem, which was solved by Euler and other mathematicians like him. And that says that basically the sum from n equals 1 to infinity of 1 over n squared, the reciprocals of the sums of the squares, that's just equal to pi squared over 6. So the left-hand side is 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared. That's going to be precisely pi squared over 6. And there are lots of ways of proving this. There's ways of proving this using sorts of integration techniques. There's also a way that's very commonly taught in universities, particularly in mathematical methods classes. People tend to use Fourier series and Parseval's identity to prove identities like this. There's also a similar one for 1 over n to the 4, I believe. But in this case, I'm going to use contour integration, which I think is a very nice result because you get to prove results like this, which just sort of pop out by choice of a very particular function, which is nice. So in this case, I'm going to define f of z, my function, to be g of z over z squared. And this g of z is going to be pi times cotangent of pi z. Remember, cotangent is just 1 over the tan function. So in other words, f of z is going to be g of z over z squared. Okay, and what am I going to do with that? I'm going to integrate my function f over the boundary of this square. And this is a square which cuts the positive real axis at n plus a half and the negative real axis at minus n plus a half. And in this case, n is an integer. In particular, it's a positive integer, i.e. a natural number. And this is a square which has side length 2n plus 1. And you can see that because this point is n plus a half and this point is n plus a half, like so. So then the side length of the square has got to be n plus a half minus n plus a half, which is just 2n plus 1. So 2n plus 1 is the side length. So basically I'm going to start at this point and traverse it anti-clockwise. And what I'm going to do is I'm going to try and look at the zeros of this function f. And the zeros of this function f are going to turn out to be precisely the integers. So they're going to be on the real line. So there's going to be essentially inside a square, which is of bounded size, then there's going to be finitely many poles inside. But when I let n go to infinity, so when I do the calculation, I'll let n go to infinity, it's actually going to encompass all the integers, which is quite nice. And let's just see how I'm going to do that. So in the first step, I'm going to do the following. By the way, when I do the integral, I'm also going to have to show that the integrals over each of these sides essentially have a zero contribution. And I might have to split the video depending on how long it is, but let's just see how things go. So let's just start. So first of all, I want to see where the poles of this function f are, but to do that, I need to find the poles of g first. So what's g? G of z, that's just equal to pi times cotangent, which is 1 over tan, but tan is sine over cos, so 1 over tan must be cosine over sine. So this is just cosine of pi z, all divided by the sine of pi z. And the poles of this function g are going to be precisely the points at which the denominator is equal to 0. So in other words, where is sine of pi z equals to 0? Well, that happens whenever I have sine of 0, or sine of pi, or sine of 2 pi, or perhaps sine of minus pi, sine of minus 2 pi. So in other words, whenever z is an integer value, like 0, 1, 2, or minus 1, or minus 2, or minus 3, then that's going to correspond to a pole. So in other words, if z, let's do it like this. So if z equals n, where n is just some integer, then I will have a pole of g. Now, a couple of questions about this pole. First of all, is it a simple pole? And by simple, I mean it has multiplicity 1. So for instance, the function 1 over z, that has a pole at 0, and it has multiplicity 1, because the power of z is just 1. There's only one instance of 0 appearing. However, if this were a power of 2, let's say, then the multiplicity of that pole at z equals 0 would have multiplicity 2. So what is the multiplicity of sine pi z? Because it's not exactly in this sort of form, so how can I tell? So what I'm going to do is I am going to let h of z be equal to sine of pi z. And we know that h of n, or in other words, sine of pi n, where n is an integer, that's just going to turn into 0. So what I'm going to do instead is I'm going to look at h prime of z. And h prime of z is just the derivative of this function with respect to z. And the derivative of sine is cosine, and using the chain rule, I'm going to get pi out front. So I'm going to get pi times cosine of pi z. And when I plug in z equals n, I'll get h prime of n, and that's equal to pi cosine pi n. And now I just have to ask myself, is this function equal to 0 at this value of n? And the answer is no, and that's because if n is an integer, I'm going to get cosine of 0, or cosine of pi, cosine 2 pi, cosine 3 pi, and cosine is not equal to 0 at that point. So for cosine to vanish, or be equal to 0, I'd need to have n equals a half, or plus or minus a half, or plus or minus 3 over 2, and so on. And n is an integer, so that definitely can't happen. So that's impossible. So that tells me that h prime of my pole is not equal to 0, but I do have that h of n is equal to 0. And that tells me that my pole has order 1. Now, if my pole had order 2, I would find that h of n was equal to 0. I'd also find that h prime of n was equal to 0. And then to verify that it was of multiplicity 2, I'd have to calculate h double prime of n and show that that was not equal to 0. And then I'd basically have to differentiate this, plug in n, and determine if it was a pole of order 2 or not. But here, I can see that h of n equals 0, h prime of n is not equal to 0, so that's sufficient to tell me that the pole, in fact, is simple, i.e. has order 1. So let's write that down. So I've got simple poles of G at z equals n, where n is an integer. So for all integer values of n, z equals n is a pole of G. So we've got the poles of G, so let's calculate the residue of G at each of those poles. So what is the residue at z equals n of G of z? Or using the residue formula, that's just the limit. Let's do that a bit neater. The limit as z approaches n of z minus the pole, which is z minus n, times G of z. And that's just the limit as z goes to n of z minus n times G of z, and G of z in this case I've defined as pi cotangent pi z, which is just pi cos pi z over sine pi z. So that's pi cosine pi z over sine pi z. And this doesn't look particularly helpful at this stage, but I'm going to do some playing around with it. So that's going to be equal to the limit as z approaches n of z minus n times pi cosine pi z, all divided by sine of pi z. And I'm going to do something unusual here. I'm going to subtract sine of pi n from the denominator. And I can do that because because n is an integer, this thing is just equal to 0, right? Because if n equals 1, 2, or minus 1, or minus 2, or n is any integer, this term is just 0. So all I've done is basically subtract 0 from sine pi z, so I haven't changed the value of this function in any way. So I haven't really affected the limit. But why have I done such a thing? Well, I want you to pay close attention to this portion of the limit. So I want to draw your attention to this bit. So why does this look familiar? Well, if I go back to my value of h prime of n, that was pi cosine pi n, and how is that related to this? Well, recall the limit definition of a derivative. So we know that h prime of n, that's the derivative of h evaluated at n, and recall that h of z, in this case I just defined as sine pi z. The derivative of h at the point n is defined in terms of the limit as z approaches n of h of z minus h of n, so that's h of z minus h of n, all divided by z minus n. That's the definition of the derivative of h at n. And that is going to be the limit as z approaches n of sine pi z minus sine pi n, all divided by z minus n. And this looks pretty familiar to what I've got in the red circle. In fact, it's just the reciprocal of what I got in the red circle. So what can I do about that? I haven't got the reciprocal here, so perhaps I can do something. Well, h prime of n is equal to this limit. So if I take reciprocals of both sides, what happens? Well, then I've got 1 over h prime of n. That's going to be equal to 1 over the limit as z approaches n of sine of pi z minus sine of pi n, all divided by z minus n. And I can do this because h prime of n is never 0, as I've just shown, because h prime of n is pi cosine pi n, which is never 0 for any integer n. Okay, so in particular, that's quite an important point because it tells me that the reciprocal function is continuous at h prime of n. So what that means is I can basically bring the reciprocal function inside because this thing isn't 0. So since it's a continuous function at h prime for all integer values of n, that tells me that that's exactly the same as the limit as z approaches n of the reciprocal of sine pi z minus sine pi n all divided by z minus n. So in this case I had the reciprocal function outside the limit and I brought it inside, which I'm allowed to do by the algebra of limits because the reciprocal function happens to be continuous at that point. But what is a reciprocal of that? That's just the limit as z approaches n of, well, the reciprocal of a fraction is just the swapping the numerator and denominator around, so that's z minus n, all divided by sine pi z minus sine of pi n. And this is exactly what I have when I was calculating the residue above. So you see, I've skipped back. So you can see that these two things are now the same. So this whole thing is going to go to h prime, or 1 over h prime of n. So in other words, that tells me that the residue at z equals n, the integer n, of g of z, that's equal to the limit as z approaches n of z minus n times, what did I have here? Times pi cos pi z times pi cosine pi z, all divided by sine pi z minus sine pi n. Now I know from the work I did above that this thing, not including the pi cos pi z, will converge as z approaches n to 1 divided by h prime of n, and obviously pi cosine pi z is going to go to pi cosine pi n. So by the algebra of limits I can just multiply those limits together, and that's going to give me 1 over h prime of n times pi cosine pi n, that's just this thing evaluated at n, and that's what? That's pi cosine pi n, but h prime of n was also pi cosine pi n. So in fact, I've got this divided by this, so two equal expressions, and the quotient of that is just going to be equal to 1. So in other words, the residue at g, or the residue of the function g at each of the integers, is always going to be 1, and that's going to be a very important fact. So how does that help me now? Well, now I want to calculate the residues. I want to look at my function f and find out where the poles are and see if that will help me find the residues of f at those poles. So recall that f of z I defined to be the complex valued function g of z, all divided by z squared. So where are the poles of this function? Well, they're going to be basically the same, with one notable difference. So let's just write that down. So if z is not equal to 0, then obviously I've got poles at z equals n. So z equals n are poles. Maybe I should write n is not equal to 0 in this case. And these are of order 1. So these are of order 1. Now you can see that the reason I set n not equal to 0 is because I've also got an extra pole, an extra double pole in fact, at z equals 0. So when z equals 0, I have a pole which is of order 3, and the reason it's 3 and not 2 is because 0 is also a pole of g. So 0 has multiplicity 1 as a pole of g, and as a pole of f it also has a multiplicity of 2. So I add the multiplicities together to get 3. 2 plus 1 is 3. So z equals 0 is a pole of order 3. Okay, well this one I think should be fairly easy to calculate the residue at. This one is a little bit more complicated, so I'll do that later. Let's look at the first one. So what I need is the residue of my function f at z equals n, and in this case n is not equal to 0, and it's an integer. Well, it has order 1, so that's just the limit as z approaches n of z minus n times f of z. That's just using the residue formula. But But what is f? F is just equal to g divided by z squared, so that's just the limit as z approaches n of z minus n times g of z divided by z squared. But look what I have here. I know that the limit as z approaches n of z minus n times g of z, that's just the residue of g, right? That was just the definition of limit of the residue of g at z equals n. And as z approaches n, 1 over z squared is definitely going to be equal to 1 over n squared, and that's fine because the point at 0 is not included. So this is just equal to the residue of g at n, which was just 1, multiplied by the limit as z approaches n of 1 over z squared, which is 1 over n squared, and that's just 1 over n squared. So you can start to see the shape of the Basel problem starting to take form, because this is where the 1 over n squared term is going to come from. And obviously when I calculate the sum over all the integers n, that's going to be where the summation comes from, but then I'm going to have to take the limit so it encompasses all the integers, and that's basically where it's going to, where the fun's going to start, if it hasn't already. Okay, so I've done the residue at, I think I've gone too far up, so I've done the residue here. The residue just ended up being 1 over n squared. Now I need to look at the residue at z equals 0, and this is probably I think perhaps the most tedious part of this calculation. So let's just do that and get it out of the way. So the residue at z equals 0 of my function f, well, 0, the pole at 0 has multiplicity 3. So recall that I'm going to have to use the formula for residues, which says that I'm going to have a constant term of 1 over n minus 1 factorial out front, where n is the multiplicity of the pole. So in this case I'm going to have 3 minus 1 factorial, which is 2 factorial, which is 2, multiplied by the limit as z approaches my pole 0 of the second derivative of my function, and the order of this derivative will be n minus 1, where n is the multiplicity of the pole. In this case I've got 3 minus 1, which is 2, so this is second derivative of z minus 0 to the power of the multiplicity of the pole, which in this case is z cubed, multiplied by my function f of z. And that's going to be equal to a half times the limit as z approaches 0 of the second derivative with respect to z of what? Well, I'm going to have z cubed here, and what is f? Well, f of z is equal to g of z divided by z squared. Okay, and what is g? Well, g, by my definition, was, let's see, g was pi cotangent pi z. So this is a half times the limit as z approaches 0 of d2 by dz squared times what? Well, z cubed divided by z squared is just z, and then I'm going to have pi cotangent pi z, which is just pi cos pi z, all divided by sine of pi z. Okay, well, there's not much I can do at this stage. So, you know, for instance, it doesn't seem like L'Hopital's rule might help at all, and plus I can't really use that because I've got derivative here. So it looks a bit difficult to calculate the derivative of this function. It might be a little bit tedious, so what can I do instead? I'm going to use the Taylor series of sine and cosine. So the Taylor series for sine, let's do sine of x first. That's just x minus x cubed over 3 factorial plus x to the 5 over 5 factorial plus higher order terms. Likewise, the Taylor series for cosine is just 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial plus higher order terms. So now I'm just going to replace x with iz, and you can prove using complex analysis that that's the Taylor series for sine with complex argument. So the sine of, I think it's pi z I'm doing, that's pi z minus pi z cubed over 3 factorial plus pi z to the 5 over 5 factorial plus higher order terms. I know it's a minus here, but I'm just using plus to essentially talk about the rest of the sum. And likewise, cosine of pi z is equal to 1 minus pi z squared over 2 factorial plus pi z to the 4 over 4 factorial, and so on. So the first thing I'm going to do is I'm going to take the Taylor series for sine pi z and plug it directly into the denominator here and see what I get. So I'm going to get the limit, well, a half times the limit as z approaches 0 of d2 by dz squared of what? I'm going to have pi z cosine pi z all divided by the Taylor series for sine pi z, which in this case is this thing at the top, and that's going to give me pi z minus pi z cubed over 3 factorial plus pi z to the 5 over 5 factorial, and I need to extend my fraction division sign, plus higher order terms. Okay, well, notice that I can cancel out a factor of pi z from the numerator and denominator. So when I do that, I get the half times the limit as z approaches 0 of d2 by dz squared. And I'm going to get cosine pi z, all divided by, well, pi z divided by pi z is 1. Pi z cubed divided by pi z is pi z squared. So I'm going to have minus pi z squared divided by 3 factorial. Likewise, for the third term in the Taylor series, I'll have pi z to the 4 over 5 factorial plus higher order terms. And I want to do a little bit better than that. I want to see if I can write 1 over 1 minus pi z squared plus blah 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 in terms of a power series. So I want to write that as, let's say, 1 plus some constant times z plus some constant times z squared, and so on. So in other words, I want a power series to replace this denominator. So recall that the geometric series for 1 over 1 minus x, and this converges if x has modulus less than 1, not that that's important here, that's just equal to 1 plus x squared plus x cubed plus dot 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 higher order terms. So if I use this formula with x equal to pi z squared over 3 factorial minus pi z to the 4 over 5 factorial plus higher order terms, then 1 over 1 minus x is going to be precisely this, right? So if I have 1 minus this series, I'm going to get 1 minus pi z squared over 3 factorial plus pi z to the 4 over 5 factorial, and so on and so forth. So 1 over 1 minus that is just going to replace that term there. So what do I get when I try to expand 1 over 1 minus x? I'm going to get 1. So in this case, 1 over 1 minus x is going to be 1 plus x, which is pi z squared over 3 factorial minus pi z to the 4 over 5 factorial plus higher order terms. That's my x term. And then I'm going to have to add x squared. So that's the same thing as the thing on the left, all squared. So that's pi z squared over 3 factorial minus pi z to the 4 over 5 factorial plus higher order terms, all squared. And what I'm going to do is I'm going to collect the coefficients of z to the 0, which in this case is just going to be 1. So collecting coefficients of like powers of z, that's going to be 1 plus, well, I'm going to have something times z. Well, am I? Well, there's nothing times z in this bracket, and there's nothing times z in this bracket. So there's no way that any contribution from either of these parentheses is going to give me a coefficient of z that isn't 0. So I'm not going to have anything times z, sorry. What about z squared? I'm clearly going to get a coefficient of z squared here. So what's that? I'm going to get pi squared over 6, because that's pi squared over 3 factorial, which is 3 times 2 times 1, which is 6. So pi squared over 6, z squared. I'm not going to get any contributions towards z squared here, because the smallest power I'm going to have from this contribution is z to the 4, because remember I'm squaring everything here. So what's the contribution towards z to the 4? I'm not going to have anything for z cubed, obviously, because there's nothing cubed here, and there's no way I can get z cubed here, because I need to have z to the power 1.5, which I don't have. So what can I do? Well, I'm going to have plus, I'm going to have a contribution of minus pi to the 4 over 5 factorial here, and also a contribution of pi squared over 3 factorial here, which is 6. So let's do it like this. That's the same as pi squared or pi to the 4 over 3 factorial squared, which is 36. And then I'm going to have minus pi to the 4 over 5 factorial squared, or just 5 factorial, which is 120. 5 times 4 times 3 times 2 times 1. All of that times z to the 4 plus higher ordered terms. By the way that you'd usually write this is big O of z to the 6. And we're going to explain in detail what this means, especially if you're following my prime numbers and their distribution series, which I want to explain that in more detail, exactly what the analytical definition of that is. But for now, just treat that as meaning higher ordered terms. And that's a big O, by the way, not a little o, which means something different. Okay, so let's simplify that. That's 1 plus pi squared over 6 z squared plus this. And let's see if I can simplify that. Well, I noticed that I can take 36 and multiply that by something to get 120. So I can write the first fraction as, well, if I multiply the top and the bottom by 10 over 3, then I'm going to get 120 as a denominator here. So that's 10 over 3 pi to the 4 over 36, or is it 120? That's 120 minus pi to the 4 over 120 times z to the 4 plus higher order terms, or big O of z to the 6 if you prefer. And that's equal to 1 plus pi squared over 6 times z squared plus what? Well, here I'm going to have 10 thirds minus 1, which is just 7 thirds pi to the 4, all divided by 120 times z to the 4 plus higher order terms. And that's just equal to 1 plus pi squared over 6 plus what? Well, multiplying the top and the bottom by 3 is going to give me 7 over 360, so that's 7 pi to the 4 over 360. 360 z to the 4 plus higher order terms. And that was the value of, just to recall, 1 over 1 minus x. So that takes care of the 1 over 1 minus stuff part of the expression. Now I just need to deal with the cosine. So I need to multiply this series I've just found by cosine. So I need to calculate basically 1 plus pi squared over 6 plus 7 pi to the 4 over 360 z to the 4. It should be, I think I'm missing some z squared terms. Yeah, so I forgot to write z squared here. So that's plus higher order terms, and I need to multiply that by the Taylor series of cosine, which in this case is just 1 minus pi squared z squared over 2 factorial, which is 2, plus pi to the 4 z to the 4 over 4 factorial, which is 24, plus higher order terms. Now, how many terms of this series do I need to calculate? Well, if I look back at my original limit, or my original expression, now I'm going to find some power series as a result of multiplying all this tedious stuff out, and then I'm going to take the second derivative. So suppose I had a term that of something times z cubed. Well, then I go and take this derivative 2 times, so I end up getting something times z, but then I take the limit as z goes to 0. So, and that's going to happen for a z cubed term, a z to the 4 term, z to the 5 term, but for a z to the 2 term or a z squared term, that isn't going to happen. So the only terms that I need to worry about are those up to and including the z squared term. So that's all I need to know. I don't need to worry about the z to the 4 parts. So the constant coefficient is just going to be 1. I'm not going to have anything times z. What about z squared? Well, I'm going to have to do, let's see, I'm going to have pi squared z squared over 6. That's going to be one contribution. So pi squared over 6. And then I'm going to have a minus pi squared over 2 coming from this bit. So minus pi squared over 2. All of that times z squared. Plus, let's write it as big O of z to the 4 Well, let's keep things a bit simpler. Let's write that as plus c times z to the 4, plus so on and so forth, just to illustrate the point. And that's 1 plus what? Well, a half is 3/6, and 1/6 minus 3/6, that's just minus 2/6, so that's minus 2 pi squared over 6 times z squared plus c times z to the 4, where c is just some real number, plus higher order terms. And that's going to give me 1 minus pi squared over 3 times z squared plus c times z to the 4 plus higher order terms. So if we then take this series that I've just found and replace this whole term inside the derivative, or after the differential operator, I'm going to get 1/2 times the limit as z approaches 0 of d2 by dz squared of the following limit, i.e. the limit above, of 1 minus pi squared over 3 z squared plus c times z to the 4 plus higher order terms. And if I calculate the derivative, that's just 1/2 times the limit as z approaches 0 of the double derivative of this stuff. Well, double derivative of 1 is just going to be 0. Here I'm going to have minus 2 pi squared over 3 times 1, so it's going to be minus 2 pi squared over 3. But for the derivative of cz to the 4, I'm going to have 4 times 3 times cz squared, or 12 cz squared, so let's write plus 12 cz squared plus higher order terms. So you can see this would be a z to the 4 term here. But when I take limit as z goes to 0, obviously this thing is going to go to 0. So that's why I didn't need to worry about what the value of c was. So this is just going to be 1/2 times minus 2 pi squared over 3. And that's going to be equal to minus pi squared over 3. And that was my residue, just to recap, of my function f of z at the pole, the triple pole, z equals 0, the pole which had multiplicity 3. So in other words, the residues of f, so let's just do the residues were, that's quite appalling handwriting, the residues were minus pi squared over 3 at z equals 0, and I had, what did I have everywhere else? I had 1 over n squared at z equals n. Z equals n, where n was some integer not equal to 0. That z backslash 0 means the integer is not including the point 0, or the element 0. Okay, so how does that help me? Well, if I go all the way back to the beginning of this video, and I look at my contour, which was over a square, then I can basically say that the integral of f over this contour is going to be 2 pi I times the sum of the residues that I just found. So in other words, let's go all the way down. The integral, the contour integral over s sub capital N, which is shorthand for my square, of f of z dz, that's going to be equal to 2 pi I times the sum of the residues which lie inside the square. So in other words, it's going to be 2 pi I times the sum. Well, let's see what I've got here. I'm going to have the residue at z equals 0 was minus pi squared over 3. So that's going to be minus pi squared over 3. That's the pole at z equals 0. So let's just write that. Z equals 0. Plus, now the residue at z equals n, the pole z equals n, was 1 over n squared. But these poles occur all the integers which lie inside the square. So this is going to be the sum of not n equals 1 from n equals 1 to infinity, but over all the integers n whose modulus is less than capital N, and n is non-zero. So don't worry about all these conditions on the sum, it won't matter in the end too much, but it's still a bit important, of 1 over n squared. So basically, each residue at 1 over n squared, I need to sum each possible residue, because it actually varies over all the integers. Okay, so now I want to let n go to infinity, So that tells me that the limit as n goes to infinity of the contour integral of s sub capital N of f of z dz, that's equal to 2 pi I times minus pi squared over 3 plus, well, if n goes to infinity, I'm going to have the sum over all possible integers n, not including 0, of 1 over n squared. Okay, now this doesn't look quite like the original sum, which is just over all the positive integers. So what I'm going to have to do is I'm going to have to split this sum into two parts. So this is just equal to 2 pi I times minus pi squared over 3 plus the summation as n goes from 1 to infinity. So if this is the positive integers, n, 1 over n squared, plus the sum as n goes from 1 to infinity, and I suppose explicitly I should use a different index, but you know what I mean here, of 1 over minus n squared. So in other words, this sum sums over all the reciprocals of the positive squares, and this sum does the same but with negative squares. So this is going to give me 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, but this sum is going to give me 1 over minus 1 squared, 1 over minus 2 squared, 1 over minus 3 squared. So it's going to cover all of the terms of this sum. But you'll notice that minus n squared, so minus n squared, is just n squared. So in fact, these two sums are the same. So this is just equal to 2 pi I times minus pi squared over 3 plus the summation, as n goes from 1 to infinity, of 1 over n squared, plus exactly the same thing. So I can actually put a plus 2 here. So it's going to be 2 times this sum, because these two sums are clearly the same. Okay, so what have I proved? I proved that the limit as n goes to infinity of the contour integral over s sub capital N of my function f of z dz is equal to 2 pi I times minus pi squared over 3 plus twice the sum as n goes from 1 to infinity of 1 over n squared. So I'm almost there. Let's just neaten this up. So I'm almost there, but I'm not quite there. So I've got the correct sum. I just need to show that this limit goes to 0. And in the next video, because I think this video has gone on far too long, I'll use the estimation lemma to show that this integral, as n goes to infinity, basically goes to 0. So I want to end up with 0 is equal to this stuff on the right, and if I do some little manipulations like divide by 2 pi I, then add pi squared over 3 to both sides, divide by 2, you'll see that the result to the Basel problem pops out rather nicely. But it's a little bit long to prove that in one video. So if you enjoyed this video, please leave a like, comment and subscribe. Make sure you stick around for part 2, which will follow this video immediately, I hope on the same day. And yeah, if you liked what you saw, please subscribe, and I'll see you in the next video. Thanks.